Hi, welcome back. So we kind of talked about the energy equation and came up with the solution where we decouple the velocity and temperature, right? And we came up, the last time we stopped, it was at this equations 12 and 13, right? And so we also came up with this, the Prandtl number and Eckert number, okay? So what we're going to do today is actually going to, today in a couple of modules, is to really understand what the Prandtl number here means and what does it sort of mean in terms of physically, what does it boil down to, okay? So because we relate a lot of things, for example, the Reynolds number, that's something you're more familiar with. So we'll also do this kind of in a similar study as to what exactly is this Prandtl number and how is it, what exactly is it, so this is your Prandtl number that, we had, and this is the Eckert number. So we'll talk about that, okay, the Prandtl number and the Eckert number. So let us begin to do that and see, how things shape up and whether we can get some more inferences from this. Okay, now before I get to that, just a little bit, what do we mean? You're going to hear this term a lot in that forced convection, forced convection. So I'm going to define that a little bit, okay? So let me write down, okay, let me first, write this topic as forced convection of constant properties, right? Now, these are the two equations which I just showed you, right? But I'm anyway still going to sort of write it down again, just for continuity, I guess, okay? So, right, this is a non-dimensionalized form. Prandtl number, right? And let's call that equation 1, okay? Okay, is equal to 1 by Prandtl number del u star del y bar square, and let's call that as 2. Okay, now what we're going to do is to write equation 1 again, in the dimensional form, okay? So basically what we're saying is that dimensional form of 1. Right, that's what I'm talking about. So we've done this math earlier. You can do this to cross-check. Okay, I'm not going through the whole drill of it. So it will look like this. So if I were to do that, it will look like this. Okay, so this is essentially the energy equation. Okay, this is the energy equation, okay, where A is equal to, right. So, what is A? A is the thermal diffusivity, okay, and lambda is something that we've said earlier. So, lambda is thermal conductivity, okay. So, we've dealt with lambda before, so I'm not writing that again. So, so A here essentially is the thermal diffusivity, okay. Now, what happens here is that, as we've emphasized earlier also, you can see here that in order to, if I were to solve this equation, this energy equation in this form, right, and if I were to get a, an expression for T across the boundary layer, I would need to know the velocity, right. I would need to know the velocity first, right. So, I would actually, so if I were to write this down, okay, let me sort of write this down. So, basically what I'm saying is to determine the temperature field, that is T, right, x, y, in the boundary layer, okay. We need to know the velocity field, okay. We need to know the velocity field, which is this, right. So, therefore, basically we are saying that there has to be a flow. So, which means that we are forcing the flow to have a velocity. So, we need the flow, we need the fluid to have a motion for us to determine the temperature field, right. So, that's why we come up with this terminology, forced convection or forced convective heat transfer, right. So, what you're basically saying is, so what this essentially means that the motion of the fluid is forced. So, you have to force the fluid to have a motion, right, so that it has a velocity field. I can calculate that, and hence I can calculate the temperature, right. So, which essentially means that motion of the fluid is forced, right. So, therefore, we say, which hence we use the terminologies forced convection, okay, and forced convective heat transfer. Forced convective heat transfer, right. Now, we will need to have some boundary conditions, of course. So, what are those boundary conditions? What are those boundary conditions? Of course, at far away from the far distance away from the wall or the plate of the surface, wherever you are looking at the temperature field, the temperature is equal to the free stream temperature, right. So, at a far distance from the wall, at a distance far away from the wall, right, that would be the right English. Okay, at a distance far away from the wall, the temperature is equal to the free stream temperature, so that the non-dimensionalized temperature difference, theta 1 basically, is 0, right. We could have a definition, or we could specify the wall temperature distribution, right. So, we could have a wall temperature distribution, easiest thing would be to make it a constant, and we will do that actually. Okay, so you could have a wall temperature distribution. You could also have the heat flux distribution at the wall. Okay, you could have a heat flux distribution at the wall, right, which is that is equal to let me write that neatly. Okay, is equal to right. So, well, actually, this is, I'm not sure if you're realizing this, but this is kind of, you know, if you have a wall temperature distribution, then it is basically, you know, the temperature of the wall directly. But if you don't, but if this is not specified, if this is the boundary condition not being used, then you could also have a boundary condition like this third one here, where you are basically, you know, the heat flux distribution. So, which is, you know, the normal component of the temperature at the wall. Okay, so this is similar to the Neumann and Dirichlet boundary conditions, you know, velocity, if you're aware of it. So that is, you know, you either you say the property that you're talking about, in this case temperature, is directly you know, specified, which is case 2 here, or the normal component, which is the Neumann, and the Dirichlet is the second one. Okay, so the Neumann boundary condition is similar to the third one actually. So that's what we're saying. So now another thing is that you could have a combination of the two. You know, you could have a combination of the two as well. So, which is basically there is a relationship between QW and tau W. Okay, so there is a relation between tau W, and this is actually called a mixed boundary condition. So this is a mixed boundary condition, right? And so basically we'll have to calculate, you know, both simultaneously, right? So temperature field and the you know, so basically temperature field at the wall and the body have to be calculated simultaneously. Okay, so that's the, you know, that's what we mean by the mixed boundary condition. Okay, so that's how we sort of go about doing that. Okay, so now let us come back to where we started out, saying that we're going to look at the effect of the we look at the effect of the Prandtl number. So this is what I'm talking about, the Prandtl number here, right? So we're talking about the Prandtl number here. So now, so let us sort of call it that. Okay, so what we're going to say here is effect of the Prandtl number. Okay, so let us see where we get to from here. Okay, now previously, okay, I mean when we did this earlier, we know that Prandtl number was defined as mu Cp by lambda, right? But just now, as we said, thermal diffusivity, we got A to be defined as lambda by rho Cp, right? So then from this expression, what I can write is, so from here I can write Cp by lambda is equal to 1 by A into rho, right? So if I use this and put it back here, so what I get is, that Prandtl number is equal to nu into 1 by A by rho, right? But we know that nu by rho is nothing but kinematic viscosity by A. So this is important. So basically what we're saying is that Prandtl number, okay, is a direct ratio, okay, I'm going to call this as 2. Okay, so Prandtl number is a direct ratio of the kinematic viscosity to the thermal diffusivity. Okay, that's interesting, right? That gives us a little bit of a physical feel for what this actually is, it's going to be like. So let us see, okay. So it is actually a physical property of the fluid, okay, and here of course, as we have seen, similar to how the Reynolds number is something that we use for subsonic flows. So Prandtl number here is, is the characteristic number for thermal boundary layer and heat transfer in forced convection, right? So that's basically what the Prandtl number is. Now, so basically what we can say now, infer from 2, right? From 2 what we can infer is that from 2. So from 2 what we can see here is that it's a ratio of transport properties of a fluid with respect to momentum, right? Because there is a momentum change across the boundary layer due to the existence of the kinematic viscosity, right? To that due to the existence of heat transfer, which is A here, thermal diffusivity. So if I were to write that down, that Prandtl number, okay, it meaning Prandtl number, okay, I can write that Prandtl number. That Prandtl number, okay, is a ratio, okay, of transport properties of a fluid, right? So there is a transport of properties of a fluid due to momentum. So with respect to momentum, and that happens due to the existence of kinematic viscosity, right, to that with respect to heat, and that is due to the thermal diffusivity. So basically we are saying that if there is a momentum, if there is there is a momentum transport, right? We've talked about this earlier. So we have a velocity profile across the boundary layer, we have a momentum transport across the boundary layer, and that is because of the existence of viscosity, right? So the transfer process of a fluid with respect to momentum, and we have a heat transfer across the boundary layer because of the existence of thermal diffusivity. So Prandtl number is basically a ratio of the transport properties of a fluid with respect to momentum to that with respect to heat, right? So now the point is that, as you can see, very easily, that if Prandtl number is very large, right? You can see from here that if Prandtl number is very large, which means that the kinematic viscosity is very large with respect to A, right? So which means that if the kinematic viscosity is very large, which means that we will have a very large boundary layer thickness, right? Which means that this change in momentum, right, or the momentum decrease that happens because the the surface pulls on the flow, right? So it slows it down. So it slows it down. So velocity is 0 at the wall. It increases to free stream away from it. All of this happens because of the nu, right? And hence, of course, there is a change in momentum. There is a decrease in the momentum. Now, so this effect, right, is quite dominating, and it extends far into the fluid. Right? So that happens if Prandtl number is very large. So, one can sort of understand that, which means that delta x, which is the boundary layer thickness, will be very large, right, if the Prandtl number is very large. So, right here again we can say that Prandtl number very large, right, implies that boundary layer thickness is very large, right. Now, similarly, of course, if the heat dominates, so when Prandtl number will be very small, right. So, Prandtl number is very small, what happens? Then the heat dominates, right. When Prandtl number is very large, that means delta x will not dominate, right. Then the thermal boundary layer will be dominating. So, we can say that thermal boundary layer is very large, or that dominates. Okay, I will expand on that a little bit right now. So, therefore, Prandtl number, okay, is also a direct measure of these two heights or these two distances, like the velocity boundary layer and the thermal boundary layer. Okay. So, Prandtl number, so therefore, Prandtl number, as we said, is the property of the fluid, right, and it gives you a ratio, idea of the ratio of transport properties with respect to momentum to that of with heat. And it is also a direct measure, of the it's also a direct measure of the boundary layer, velocity boundary layer thickness to the thermal boundary layer thickness. Okay. So, we can say that this is the velocity boundary layer thickness to the thermal boundary layer thickness, right. Now, so so that's that's to talk about what exactly so we're trying to basically understand what physically, or what exactly we came up with this number, the Prandtl number. Now we need to figure out what exactly that means, and whether we can plot things against the Prandtl layer and make inferences out of it, like we do for a Reynolds number, right. So that's what we're trying to do here. Okay. Now the next thing, now for a flat plate, okay, at zero incidence, okay, for a flat plate right, with Prandtl number equal to 1, okay, which means that is what nu is equal to A, right. And we had a boundary condition. So, the wall bound temperature is, we are going to use this, okay. Then the differential equations, okay, then the differential equations, if you see, I am reproducing this, you can look this up yourself. We've sort of, okay. Okay, so this is for the velocity. So, this is for a flat plate, okay, at zero incidence, okay, at flat plate at zero incidence, basically that it's in in line, the flat plate is kept in line with the free stream. It's aligned with the free stream. The Prandtl number is 1, right, and the wall temperature is constant, right. Then the differential equations turn out to be like this, okay. And here, well, basically, as you can see, that they're actually identical, right? They're actually identical, and in this case, right, in the number 1, that they're identical. The differential equations are identical, and the secondly, in this case, delta right, that is the velocity and thermal boundary layers, the layer thicknesses are same. Okay, that is so that's for a flat plate. So that's what it comes down to if I were to look at Prandtl numbers. If I had a Prandtl number which is equal to 1, right, and I use a wall temperature which is constant, then what it boils down to is that the equations look they're exactly identical. Okay, and the two thermal and velocity boundary layer thicknesses are same. Okay, now that, please remember that this is essentially for the conditions that I have said. It's a flat plate. It's a flat plate. It's at 0 incidence. Prandtl number is 1, and tau wall is constant. Okay, so now for any other flow, however, okay. Given the conditions, so these are of the same order of magnitude, okay. So they're not really poles apart or anything, okay. So now what we're going to do is sort of continue on this a little bit and talk about two very important, two sort of limiting cases, right. That's kind of just talked about that. This is one is the Prandtl number is very large. And secondly, the Prandtl number is very small. Okay, so you kind of have an idea what that means. Now, because what happens here is that it brings about a lot of simplification. Severe simplification in the type of equations that in the type of solutions that we can come up with that, and formula actually, and therefore it's of a lot of interest. Okay, so I think that is something that we will start looking at, and so what I will do is I will stop here at this moment and take that up from the next in the next module. Okay, so I will kind of see you there. So let's see. So if I were to Sorry, I forgot to make this full screen right at the beginning. I hope we kind of got that. Okay, so so basically we talked about forced convection, and then we came up here. We talked about the thermal diffusivity. We wrote down the dimensional form of the energy equation. We got that, and we talked about why we're saying what exactly does the term forced convection mean, even, right? So forced convective heat transfer, right? We looked at what kind of boundary conditions are possible, okay? And so now we've started talking about the effect of the Prandtl number, okay? So we will stop here and take it up in the next one. So thanks.